I'll do is turn this, and then if I can write on the board, she'll be able to see it. Means I need to put this over here. So you can't see. Okay, we'll see how that works. And we'll get my calculus stuff. Okay, so we're halfway through the exploration 2-1. You'll have that handout. Yeah. Yeah. We're working on 2-1. We did half of it yesterday, so we're starting on number 5 today. Did you got the data thing here, right? Uh-oh, I gotta get my calculator too. I'm going to fill in the data table so we can take a look at everything. I think I still have it in here. Yes. All the way down to 3.5. Okay, so 1.25, 1.36, 1.49, 1.64, 1.81. This is interesting data, I think, just because you see these decimal parts are perfect squares. That's 5 squared and 6 squared and 7 squared and 8 squared. And interesting. And at 3, we have an error. And then 3.1, 2.21. It still follows a pattern because remember we said that this is really close to 2, that the limit looks like it should be 2. And so 2.00, that would be like 10 squared, 100, and then 121 and 144 for the squares, 2.69, yeah. 2.96 and 3.25. Okay, so you got all the data now? And it says, between what two numbers does f of x stay when x is kept in the open interval between 2.5 and 3.5? So this column is x, and this column is f of x. And so if you keep x between 2.5 and 3.5, which is 3 plus or minus 0.5, right? Then, I'm sorry, yeah, 3. Then what does y stay between? What they're asking. If you keep x in these two values, between these two values, what does y stay between? And so y is going to stay between 1.25 and 3.25. That makes sense? It says open interval, so We don't put a little equal sign here, because that will make it a closed interval. Simplify the fraction for f of x. Okay, so our fraction, or basically our equation started out as x cubed minus 7x squared plus 17x plus 5 minus 15, rather, over x minus 3. Okay, how can we simplify that? We've done it before. We've got a polynomial. We're dividing by a little binomial. Dividing, division.
Dividing the x, because like there's an x, and you can take that out and divide it.
But there's not x on this one.
Well, you would have to keep that.
You can't take an x out of everything unless everything has an x to take out of. Otherwise, you're done. But we've done division. We've even done synthetic division. Remember that? Did I make sure I copied it right before I go through all the, or was that part of COVID-19 and we didn't do synthetic division? We did do it. Okay. Okay, so that means we do this thing, right? And what do we put right here? 3, positive 3. Am I standing? Yeah, I'm standing in the way. And then we're going to have 1 and negative 7 and 17 and negative 15, right? So bring the 1 down. Then we multiply 3 times 1 is 3. And we add those, negative 4. 3 times negative 4 is negative 12. Then we add that and we get 5. 3 times 5 is 15. And we add those, we get 0. We love synthetic division, which means that this whole thing right here, when you simplify it, you end up with 1x squared minus 4x plus 5, right? Okay, and then it says to solve numerically to find the two numbers close to 3 between which x must be kept if f of x is to stay between 1.99 and 2.01. And what do they mean by numerically? Solve numerically. It's not algebraically, but what we can do is we can put f of x close to, let's say 1.99. We can, f of x is x squared minus 4x plus 5. Well, let's, instead of, if we put 1.99 here, then we can solve for x. And we can also do that for 2.01. How do we solve? Okay, well, let's say 0 on this side. So we're going to subtract 1.99 on both sides. This is number 6. We're trying to find what we're going to find the two. Actually, we're doing this algebraically, and they wanted us to do it numerically. I always tend to do it algebraically. Okay, so numerically, I think what they want to do, this is the same thing as this data right here, except this would actually give us a value at 3, right? Because we don't have any division. Let's just do this. What would happen if we did put 3 into this equation? And 9 minus 12 plus 5. Okay. Right? Which is what we said our limit was probably going to be. In fact, these look identical, except this one has the removable discontinuity, and this one doesn't. That's the only difference between these two when you graph them. They want to know, like here, we were keeping, we had with 3 plus or minus 0.5. They want to know, and over here we had 2 plus or minus what? to 1.25. A much bigger difference there. Okay, in other words, y is varying more than x is. And so they want to know, well, what's going to happen if you go between 1.99 and 2.01. So what we need to do is change this data table. And we want f of x, we want this over here to be like close to 1.99 and 2.01. So we need to see how we need to adjust this side so we can get these values. Okay. So what you can do, let's give it a shot. Try to go to table set and start it at 3. And this was at 0.1, right? Plus or minus 0.1. Let's do plus or minus 0.01. Get our table. And we're looking for 1.99, but instead, we use a different color here. If we use 2.99 and 3.01, we've got 1.9801 and 2.0201. Is that as close as these numbers are to 2? Not really. This is like 0.01 away, and this is like 0.02 away. So we need to get closer. So let's go to 0.001. 0.001. And then hit table. Okay, now we have, hang on, I didn't start it at 3. Scroll up. We have 2.999 and 3.001, and I get 1.998 and 2.002. So it's even closer, right? What I'm going to do is I'm going to look at my numbers even before that. I'm going to change my table here. So at 2.99, we got 2.998, 2.997, 2.996, and at 2.995, I have 1.990. Okay, which is exactly what I wanted for this, right? And if I go over here, go down, I'm trying to get to 2.01. 3.002, 3.003, 3.004, 3.005. I have 2.010, which is what this is. Okay, see what I did? And so so according to this, if I want my f of x to equal 2 plus or minus 0.01, right? Then x, what does x have to be? It has to be 3 plus or minus 0.005. Does that make sense? 0.005. Okay, so that's what you have for number. And we're going to do several of those. This, and numerically is doing it with this table like that, kind of trial and error. You can do it the algebraic way, and we'll probably do that later. And it's interesting because this is not as big a difference as this x value is. By changing the x just a little bit, we change the y a lot more. Does that make sense? And when you get into like quality control, that kind of thing, where they're looking at tolerances, these kind of things are important in order to pass inspection, you know. And so then in 7, they say how far from x equals 3 are the two values of x? And we said 0.005. So that's what you're looking for number 7. Number 8 says, for the statement, if x is within blank units of 3, but not equal to 3, then f of x is within 0.01 unit of 2. Write the largest number that can go in the blank, and that would be the 0.005. In the blank on number 8. And then look at the formal definition there, number 9. If you recall the informal definition, you go back to that and read it. L is the limit of f of x as x approaches c if and only if L is the one number you can keep f of x arbitrarily close to just by keeping x close enough to c but not equal to c. Remember that? So now we have something a little bit different here. It says L is the limit as x approaches c. You see where they wrote that? L equals, and you do this LIM as x approaches c of f of x, if and only if for any positive number delta, no matter how small, there's a positive number, I'm sorry, I said it is epsilon. For any positive number epsilon, the little e looking thing is an epsilon, no matter how small, there is a positive number delta such that if x is within delta units of c, but not equal to c, then f of x is within epsilon units of L. So we have L, C, epsilon, delta. They all appear in problem 8, which is which. So in the problem we've just done, well, we found this stuff right here. L is 2. Okay, L is 2. That's what our limit was. C is the x value, 3. C equals 3. And epsilon is how far away you are from the y value. So that's 0.01. So epsilon is 0.01. And then delta is how far you are away from the x value, and that's 0.005. That's the little delta, which is, you write that little symbol, looks like an S, maybe. Okay. So now I'm going to hand out. Let me get my cat. And that out. They've already got one. This is typed out big, so you can put it like, tape it to your windshield.
This is what you did.
Yeah.
For number 9, what was L?
L was 2. That's what the y value was trying to be, but that's an error. Or you can put it on your locker, or in your binder, or somewhere where you can, it'll help you memorize. It's probably the toughest thing you'll have to do the entire course is memorize that. The delta. And on the paper, it was what x was, how close you had to get to x, 0.000.
Wait, can you go over like what everything is?
Yes. I
So
will.
like the little.
Yeah, I'm going to actually draw it. And because it visually, it helps. You can understand it a lot better. So let me go to my graph. Okay, and I'm going to draw. And you had this sketched on number earlier, number whatever. So I'm going to do the exact same sketch. One, 2, 3, 4, 5. 1, 2, 3, 4, 5. So kind of about right there, and then at 3, it's up here. So okay, so we had that graph, and 3, that's what C is right there. And if you remember, the original graph had a removable discontinuity there. Okay, make sense? And this is 2. And they're saying for X, if you went 0.5 away, like we were doing, let's see, no, that was 0.5. I want to do this one right here. This is the 0.001. If you go this way or this way, 0.001, so it's a little off. So that means that this distance here, and right here, yeah, this distance in between here is delta. All right, that makes sense? So we went to 3.001. We're looking at this right here. 3.001 is 2.999. Okay, and the y values that corresponded to that are these right here. Mine's not very to scale, which is 2.002 and 1.998. And so we had a difference here. We call that an epsilon of 0.001. Let's see. 1, nope, 2. No, we wanted, yeah, I'm sorry, 9. We wanted 0.001. Is that what I had earlier for epsilon of the 1? Yeah. Okay. So does that make sense a little bit more? And if it doesn't, that's okay, because we're going to do another exploration here that's going to help. It's going to kind of go through this again. Mainly what I want you to see is if you're at 3 and 2, at 3, there is no y value. It's supposed to be 2. It's purpose. Remember purpose and action from yesterday's little story? It looks like that this graph is trying to be 2 right at 3, but it's actually undefined. But it looks like its purpose is 2, and that's what we call the limit. Okay, and so we're trying to say, well, let's make sure that, you know, we're going to get this limit. That means that as you get closer and closer to 3 on your graph, when x gets closer and closer to 3, y is also getting closer and closer to something. Okay, and they approach the 2 and the 3 differently depending on the graph. And so they're saying that 2 is the limit of this function when x is 3, if and only if there's a value epsilon. Yeah, that if there is a value here that no matter how small, and you have a delta value over here also, no matter how small. We'll see some examples of where that doesn't work. Any other questions? That's kind of so weird. So I'm going to pass. Actually, what I want to do. I think doing the exploration is going to be more useful. I'm going to pass out exploration 2 too. Not on back this time.
Let's try this one in.
Yeah, we can wait till we. Okay, now you get to actually do some drawing. So f is a function whose graph is shown there, and you notice the graph and you notice the discontinuity on it. Let's do this here. And this concept is pretty abstract, so be patient with yourself about it soaking in and learning it. Okay, so let's go here. Continuity. I was like at 5. Okay, the limit of f of x as x approaches 5 is equal to 7. So in other words, you look at this function, and what does it look like it's trying to do at when x is 5? What does it look like the y value is trying to be? 7, although it's not 7 because there's a discontinuity there. But it's trying to be, so the limit is 7. And even if there was no discontinuity and it was just a straight line, smooth line, and continuous line, the limit would still be 7. Okay, but now the function value would also be 7. But for this one, the function value is not 7 because of the discontinuity. So write the definition of limit as it applies to f at this point. Okay, so we would say, let me get the. We would say 7 equals the limit as x approaches 5 of f of x. We're not given an equation for it, at least not yet. So we'll just call it f of x. If and only if, put IFF, for any positive number. Actually, what you can do is you can say for any epsilon greater than 0, that means positive, right? It's easier to write than positive number greater than 0. Okay, for any positive number epsilon, no matter how small, there is a positive number delta. There is, and I'll just put a delta greater than 0, such that if x is within delta units of c, in this case c is 5, but not equal to 5, and so you could say not equal to the line like that, then f of x is within epsilon units of L. And in this case, L is 7. So that's what you want for number 1. You should do that good. So now it says that epsilon equals 1. From the graph, estimate how close to 5 on the left side x must be kept in order for f of x to be within epsilon units of 7. Okay, so what we're going to do, if epsilon is 1, we're going to go up here to where, okay, this should probably go like this, because it's above the 8. Okay, here's 8, right? And down here is 6. And they want us to go left side. Okay, so go up to the 8 and draw a line over to your function. Okay, start at 8. this over. And then draw a line straight down. You might want to use your ruler and see where that ends up right there.
Is this for number 2?
Yes. And so from there, from 7 to 8 is our epsilon. In this case, it's equal to 1. And so they're saying, what would delta have to be for number 2? How close to 5 on the left side x must be kept in order for f of x to be within 1 unit. Okay, so what did y'all get when you drew it down like that? Okay, so how far away is that from 5? Like it's 1, 2 point something away. Yeah, 3 units away. Here's 5, so 1, 2, 2.2, something. So that's what the answer is for number 2, is how far away from 5 that is. It's 2.2, 2.3 units away from 5. 1, 2, and then a little bit. That makes sense?
Mm-hmm.
Yeah. Okay, good. From the graph, estimate how close 5 on the right side x must be kept in order for f of x to be within 1 unit of 7. Okay, so now we're going to go down to 6. And you can draw a line all the way straight across horizontally to the function. And then go straight down and see what this delta is. And it may not be the same delta. In fact, it probably isn't. I think it's much smaller.
Wait, we're finding how far away it is from 7.
You went down to 1 because epsilon has to be 1, right? Because that's what they said. Epsilon equals 1. And so then you're going over here and you're seeing when you come down how far away that is from 5. So we have delta equals 0.1. Here. I don't know. That's the one. Yeah, no, yeah. It's a difference and how far away from 5 it is. Our 1 it might be. So the delta is the 0.9. They're asking how far away from 5 do you have, can you get? Yeah. So you can, most of y'all are getting about 0.9 right here. Okay. And so for E or epsilon equal to 1, approximately what must delta be equal to in the definition of the limit in order for f of x to be within epsilon units of 7 whenever x is within delta units of 5. Okay, so what they're doing there, they're saying, if I want to make sure that I stay 1 unit away from 7, I want to make sure for sure that I'm never more than 1 unit away from 7. How close do I have to stay to 5? And if I said, well, I can stay within 2.2, but what if I went 2.2 units this way? That would not work, right? And so what I want to do is err on the cautious side and say, well, I don't want my delta to be any more than 0.9. I know that if I stay within 0.9 on either side, I'll for sure stay within this epsilon of 1. That makes sense? So when you find the delta on both sides, the largest you want it to be is the smaller number. That makes sense, kind of larger, smaller. The largest you want delta to be is the smaller number. And so that's what you're going to have, because that'll guarantee no matter what, you're going to stay within 1 unit of 7 up there. So that's what number 4 is. So you look at the right side, you look at the left side, you see which one's smaller, and that's what your delta should be. Because at first it looked like I had two deltas, right? A delta on the left and a delta on the right. You always go with the smaller delta. It's the actual delta. That will ensure that your y value is going to stay where it needs to be. Now number 5 is where we get into some algebra. The equation of the function graph is f of x equals 5 minus 2 times x minus 6 cubed root for x not equal to 5. Okay, because for x not equal to 5, we don't have a value. So they actually specified that to make an open circle there, right? So calculate precisely the value of delta right here, okay? And so let me show you what it looks like. Let me draw this over here. Okay, so this point here is as far away from 5 and 7 as we want to get, right? And so, and if this point is, that really isn't a point, but if it were a point, it'd be 5, 7, right? What would this one be? It'd be 5 plus 0.09, right? I mean 0.9. So 5.9, comma, and then it would be, so here we're saying 5 plus delta, and then this is 6. Okay, and so, and that right there is 7 minus epsilon, right? Okay, and so what we're going to do is go back to the equation. Where do they have the equation? Okay, but this right here, we really, that's what we estimated. We just looked and said, oh, it looks like about 0.9. Maybe it was a whole 1, or maybe it was 0.8. We don't know. So that was an estimate. So what we need to do is we want to find what that point is. So what we're going to do here is we're going to, for f of x, instead of saying that means the y value, we're going to say, I'll go ahead and put the 7 minus epsilon equals 5 minus 2. And then we're going to say 5 plus delta. Okay, we think it's 0.9, but we're going to find out for sure what it is. We're going to solve for delta. And that's, let me do this. So if I call this f of x, if I called that y, then what we're doing is, and for y, we're replacing it with the limit minus epsilon. And we're replacing x with the c value plus delta. And it's not always necessarily going to be minus epsilon. It might be plus epsilon. It kind of depends on which way makes you get closer to the value over here. Now can we, and here we know what epsilon is. We know that epsilon is equal to 1. So we're going to just go ahead and put 6 equals 5 minus 2. And then when we have 5 plus delta minus 6, we can simplify that. 5 minus 6 is negative 1. So I can put delta minus 1 for the 1/3. See what I did there? Okay, now can we solve for delta? I'm going to go back up here so I can be well on camera. Hopefully you'll be able to see it too. Okay, so let's subtract 5 from both sides. That'll give me 1 equals negative 2 delta minus 1 to the 1/3. Now what do I do? Divide by 2, by -2. When is the time? This class. You have the schedule behind you. What is that? This class over. 25. Okay, good. Okay, now we still want delta, so what are we going to do to both sides? We got to get rid of this 1/3. Remember how to do that? Cube both sides. This is kind of like a square root, but it's a cubed root. And the way you get rid of a square root is square both sides. So we're going to cube both sides. So that'll get rid of that. And so I'll have -1/8 equal delta minus 1. Now we can add 1 to both sides. And we get, what's 1 minus an 8? 7/8? And what's that in decimals? Close to 0.9.
0.875.
0.875. Yeah. So it wasn't 0.9 exactly, it rounded to 0.9, but it was actually 0.875. So if you want to make sure that your y value is gonna stay within 1 unit of 7, you need to make sure your x value stays within 0.875 units of 5. That makes sense. It'll get all mixed up and we'll have to go over it again more, but hopefully it's making some sense. Okay. Now look at number 6. We have to do some more algebra. What if E is 0.01? Here, epsilon was 1. That's a pretty big range. You're going from 6 to 8. Let's bring it in a little bit. Make epsilon equal to 0.01. Let's do the same thing and see what we get. Okay. So, we're going to do this. Okay, so this part. We can start from this again. Remember, we replaced y with 7 minus epsilon and x with 5 plus delta. We want to solve for delta. Now this time, epsilon, they say, is 0.01. Okay, for number 6. And so we're going to say 7 minus 0.01 equals 5 minus 2, 5 plus delta, minus 6 to the 1/3. So now solve for delta. So see if you can do that on your own, because it's the same algebra we used a minute ago. Okay, let's do it like this. Okay, so we're gonna have that. 7 minus 101 equals 5 minus 2. 5 plus delta minus 6 1/3. And I'm gonna double check that. So this becomes 6.99. And this becomes delta minus 1. Then I can subtract 5. And I get 1.99 equals -2 delta minus 1 1/3. And divide by -2. Okay, so let's get the calculator. Double checking again. Divided by 2. By -2. Negative 0.995. I want to cube everything. And it stays negative. 0.985. Then we're going to add 1. And you get 0.014925, etc. Which is pretty close to 0.015. Okay. So you see the difference between the epsilon and delta. And so that's what our delta is. Equals delta. Okay, now look at 7. 7 says you got to do all this math, but leave epsilon as epsilon. And then you'll have an answer for delta that has epsilon in the answer. Okay, so let's try that. Everybody done with this? In fact, I'm just gonna go here from this equation. And so I'm gonna subtract 5, and I get 2 minus epsilon. Negative 2, minus 1, 1/3, 2. 2 minus, I'll put a negative 2 minus epsilon over 2 equals 1 minus 1. And then 2, negative 2 minus epsilon over 2 cubed plus 1 equals delta. That's pretty much what y'all got? Yeah. That means I could pick any tiny little number for epsilon any amount that I want to stay close to 7 over there. And then from this, find out, well, how close do I need to keep x close to 5? And that would tell me. Also in the notation, you see my deltas vary. And I've seen people do this for delta, which is kind of weird. Also epsilon, you'll see even this book switches back and forth. It'll make this symbol and this symbol. Okay. What did you say, 25? 95 is when we get out? So we have 5 more minutes. Okay, so if you have those two finished, you go ahead and staple them, put them on the desk.
Do you want us to do the last one?
So what did you learn? If you can, yeah. If you feel like you learned something there. And then we got a minute. I want to take a look at page 34. So go ahead and get those turned in and look at page 34 just for a second. Any more here? Beginning of chapter 2, and chapter 2, the title, see on page 31, is properties of limits. So we're going to be focusing in on the limits themselves for now, and then we'll come back later to more derivatives and more intervals. Okay. And then page 32 is kind of an overview. You take a look at that, and they have a really good picture on page 32 of a graph, and it shows what delta is, and it shows what epsilon is. Okay, so that's something you can flip back to and kind of refresh your memory on the drawing. And then on page 33, they're doing the numerical approach to the definition of the limit. They kind of go through the same thing that we did on exploration 2.1. So, and then they have a couple others with the sign in it that are kind of interesting because the two functions are similar in some ways, but different in interesting ways. But we're going to go on to page 34 tomorrow, well, Monday. And if you see on page 34, there's that formal definition of a limit again. And I think that's where I got, where I printed out the thing that I gave you, because they have the greater than 0. And so, and they have notes below that saying how the limit of f of x as x approaches c, how you write that in shorthand. The limit of f of x as x approaches c. That's a shorthand way of doing that. And then how the delta, the greater than sign means for any positive number. And then they have about the restriction for x not equal to c. Because if you make x equal to c, you might get division by 0. Okay. And so we'll go through the examples and do some more problems in set problem 2.2 starting next week. Any questions? All righty, well then you can clean your desk off and go to your next class. And I will stop